Today we continue talking about Kalman filter, and standard Kalman filter is really important. I try to do everything for you understand the two-type Kalman filter, the standard Kalman filter and unscented Kalman filter. This is really important for the autonomous robot or autonomous vehicle. I hope you understand, and when you look at the application in the real world, you quite understand how it works. To me, it takes me so long time to understand extended Kalman filter and unscented Kalman filter because the map inside is quite very difficult. Okay, we recap the last video. We already know about the formula, extended Kalman filter formula. The differences between the standard Kalman filter and extended Kalman filter is the function, linear function and nonlinear function, right? And the measurement function, right, is the nonlinear, right? So Kalman filter cannot use, the standard Kalman filter cannot use when the measurement right here and the state transition function are nonlinear. So because the result is non-Gaussian distribution, right? So extended Kalman filter help us to solve that problem. They use the linear approximation to update the covariance of the estimate. The linear approximation is the first two terms of the Taylor series. If you don't know about Taylor series, that's I have the link last video to see how the Taylor series. And one more important in the extended Kalman filter is Jacobian. With the matrix of partial derivatives contain the partial derivative of each dimension with respect to each state variable. Okay, I go back a little bit right here. You see what the difference? You can see the difference in the standard Kalman filter and extended Kalman filter here. The red right here we use for standard Kalman filter, right? For the linear function, right? For the extended Kalman filter, we don't use anymore. We had to use different. We had to use the nonlinear function right here, right? And how to calculate the measurement function? We had to use the linear approximation, Taylor series, and the Jacobian. It's harder to get the measurement function, right? And one example right here I want to show you because you have to clearly understand how we apply the extended Kalman filter for the problem, not only the vehicle problem, for example drone problem. If you use a drone, okay, how we measure the distance from here, from drone to the world, and we mean travel the world, and how to know let's drone now we out the building or not. Okay, so how we got the distance from here, from drone to the world, we have to build up the measurement function, right? The measurement function right here, you see, we can use the geometry map problem right here. You show it. We can call the angle right here a phi, and you can calculate the distance from drone to the world. How much from the evening world minus I divide to cosine of the phi, right? That's a function, measurement function, right? So what do you think this function? This is a linear function or no? This is a non-linear function, right? So we have to use the extended Kalman filter for our estimation, right? In this process, we linearize the function. So how to do that? You already know we use the Jacobian to get the measurement model, right? So Jacobian, how Jacobian say we had to derivative, partial derivative for each state variable right here. In this problem is the angle phi, the velocity, right? Angle velocity, and the height, right? So We got the measurement function right here. We can calculate h function right here, right? And from that we can operate the covariance quickly, right? So the common feature help us to solve the problem, right? We have the h function right here. We calculate the h right here, the blue color right here, this measurement function, and we operate the state variable and covariant nonlinear function, right? So that's the small example. You see, we can apply extended common filter to show any problem. And in any video, I will always remind you to step of the common filter. In common filter, it's always had to important step state prediction and measurement update, right? So for example, right here, the autonomous vehicle tracking the object on the road, right here, for example, pedestrian. So how to apply the common filter tracking the pedestrian on the road? How to estimate the state of the pedestrian on the road? And so in the state prediction, we use the information we have to predict the state of the pedestrian until the next measurement arrives, right? And after the measurement arrives, they use the measurement update, right? They use the new observation to correct our belief about the state of the pedestrian and continues prediction and measurement update again. So, and in this video, I focus a little bit about the sensor fusion. Sensor fusion, you combine the data from another different type of sensor and you update the measurement, right? So for example, right here we have the two types of sensor, the sensor 1 and sensor 2 at the time k. How to estimation at the time k minus 1 to estimate k? We use sensor 1 or estimation from at the time k to estimation at the time k plus 1. It means each sensor have own prediction update, right? So the belief about pedestrian's position and velocity is updated as synchronously each time the measurement is received regardless of the source sensor, right? So here's the arbiter I will talk today. We use the fusion sensor right here with two types sensor, lidar sensor and radar sensor, right? They provide the data, and after the first measurement, they trigger the common filter block right here, and common filter will prediction, and they get the data for one of them, either one, the laser, or you can use radar to update measurement. Okay, I will tell the detail how it works and coding in this case. Okay, pay attention about this. Really interesting. I like it. Okay, and how does it work? For example, at time k, right, we have the sk and bk. It means state variable k and covariant k. So at the time k plus 1, it means we had to prediction, right? We had to prediction time k plus 1, right? After prediction, we got the first measurement update. What is the measurement from the sensor, and we update the value. We got the state variable and the covariant time k plus 1. Okay, so what the time k plus 2, we also do the same thing. We prediction. Okay, we prediction time k plus 2. Okay, and after, and as soon as we get the next measurement update, we will update measurement, right? What's the different thing right here? I told you we maybe get the value from the radar measurement value for update measurement, right? In this case, for time k plus 2. So because we use the fusion sensor, so either one value from the laser or the radar we can use to for update the measurement, right? Uh, right here you see, but the different thing right here we use the remember different thing right here. If we use the lidar, we we use the Cartesian, right, coordinate system. If we use the radar, we use the polar coordinate system. Yeah, that's a little bit different. And how we mapping the value from polar coordinate system to the Cartesian, I tell you later for calculation. Okay, so we look at it. I summarize right here. At the time k, you have the sk, bk, the state variable, and covariant k. At time k plus 1, we apply the Kalman filter prediction, and after first measurement, for example, L right here is a laser. We update measurement. We got the measurement as time k plus 1 and b. After that, we continue prediction time k plus 2, and we got the measurement from sensor right here. For example, radar, right? And we update the value for the measurement. Okay, it's time k plus 2, right? So continue for s time k plus 3 and b. We do the same thing, right? So we continue to go. I want to remind you a little bit about the third dimension. Okay, third dimension, the one dimension Kalman filter again. For example, with the pedestrian, they have the one state variable described by position and velocity right here. How the state change from time k plus minus 1 to k. And we have the linear motion model for this one. You remember that time we built up for the mobile robot, okay? In a localized mobile robot, right? We have the linear model function right here. You can put the new position equal the old position plus the displacement, right? After time delta t, right? And the right here we assume the constant velocity, right? And from here we can change to state space vector. I think you know how to do that, right? It's easy. You look at the function, look at it, right? P and V, you have the coefficient right here, 1, right? 0 and delta t and 1, okay? Because you multiply together is the same right here. So, and the second one is measurement function, right? Z, right? And we have the state function right here. And to apply the Kalman filter, you remember we have the state transition function and measurement function. Two of these functions had to be linear function, right? So we have the fs, or state variable right here equal to fs plus with noise, right? And the measurement function right here, they also have hs, z equal hs plus with the omega is here is a noise. We to remember this mu and omega is the Gaussian distribution with the mean equal 0 and covariance is equal Q and R. Q is the noise for process noise. You remember that in the it's in the Kalman filter or Kalman filter. I already mentioned about the Q or R. R here is the measurement noise, right? So, and in the 1D Kalman filter, standard Kalman filter, you already know about this function for the prediction, two types of the step image prediction and the update. I mean, Kalman filter prediction, you already know about this function, right? F prime equal F S plus V mu and B prime is covariance, right? It's plus with the noise right here, and Kalman filter update all this equation. So right here, remember the Q right here is the process noise. It's referred to uncertainty in the prediction step. Remember that we assume the object travels at the constant velocity, but in reality, the objects might accelerate or decelerate. Okay, so mu, it means right here we say that's a Gaussian distribution with a mean zero and covariance Q, right? Remember that. And in the update, we have the K, right? K matrix, right? This the we often call the Kalman filter gain. Kalman filter gains is combine the uncertainty where we think covariant with the uncertainty of our sensor measurement R. Right here, K is our sensor measurement is very uncertainty, but in the Kalman filter, the Kalman filter will give more the ways where we think we are the S prime. It means if our sensor measurement is uncertain, the case may put more weight into the state prediction. And another way, if we think we are uncertain, right? We think we are uncertain. The Kalman filter will put more weight on the sensor measurement Z. I mean either one. One, we put more weight on the Z on the measurement value, or we put the weight onto the state prediction. One of them. I already talked in the last video analyze the Kalman filter equation. Okay, the constraint of Kalman filter equation, right? So, and in the measurement we have the noise. We call the measurement noise. Refer to uncertainty in the sensor measurement. So we also define the Gaussian distribution with the mean zero and covariance R. The measurement noise comes from uncertainty of sensor measurement, right? And one more thing we talk right here is the BU item right here. Normally B times U right here is equal to 0. Why? Because BU present for update position of the car due to internal force of the motor. So because we don't know this value, we would not able to model the internal force of the other object. So we set the B times U is equal to 0. But mu we can model this value because that's the trend. When we check in the object can change the acceleration, can slowly or faster or increasing acceleration, decreasing the acceleration, so we can model this value, this noise, right? So go back to the model. So now we start prediction step, right? In the Kalman filter, we start for the prediction step. So in prediction step, how we calculate we predict the S and P. That's our purpose, right? So in this example, the autonomous vehicle, we're tracking the pedestrian. The pedestrians right now, they have the position PS and PY. In each position, they have velocity VS and VY equivalent, right? So we have the state vector right here, for dimension right here, PS, PY, VS, VY, right? At time t equal k plus 1, they move to here, right? So we build up the linear motion model, right? So how do we do the similar for 1D, but right now we have the velocity S and Y too. So remember right here, you have the linear function, right? PS equal previous position plus distance, right? After time t, py is the same thing, and velocities, new velocity, old velocity plus, right? I told you this one later, okay? The VPS, VPY, VS, and VY. But remember, linear function, model function right here, they have the position, new position, old position plus displacement, right? And new velocity equal velocity because we assume this constant velocity. The velocity do not change, right? So, and we have the state vector S for dimension right here, the linear motion right here, and from here we can change to state space. Alright, last time we only one dimension is easy 2 by 2. Right now we have 4D, we have 4 by 4. The app look at the transition function right here. You see S prime and F transition state matrix S and new part right here, and we talk this one later. I hope you can know how to get the state space right here. You can look at this PS, BY coefficient before the variable right here. You have the PS1 right here. It's easy, and the second is 0, third equation 0, 0. And right here you have the continued PY. PY's don't have in the first function 0. In the second function is 1. The third 0, 0. 0, 0, okay, and continue. You have the coefficient for this Vs right here, delta t, okay. For the second equation don't have 0, okay. Vs is 1 right here, and 0 is last equation, and continue. We have the Vy in the first equation we don't have 0. The second equation we have the delta t, and the third equation we don't have 0, and the last equation is 1, right? And we plus with a new component right here. So it's easy to get a state space function, but remember this linear motion model, you have to know about this. Okay, right now you already have this, the formula right, S prime equal Fs, right? So in and we always check the problem in the step of the observation is the same. It means the delta t is always the same, right? Between the old and the new observation is the same, but in the reality, in the real world, the time is different. The time between the two observations is different. Delta t1, delta t2, delta t3, delta t4, right? And in the first dimension, you apply this, for example, with the mu right here. Mu, I told you many times, is a process noise, but we always assume the process noise, the motion noise right here is equal 0 for the first dimension, right? But in the real world, this one is mean they because the object can move slowly or move faster, they can increasing and decreasing the acceleration. So we have the motion noise right here, okay? So how to deprive the motion noise? That's the thing. How to deprive the mu right here, the motion noise? How we know how it look like in this formula? So we had to deprive that formula. So from kinematic equation, we have the new part right here, VPS, VPY, VVS, and VVY. That's the normal distribution with the mean 0 and process noise Q. You remember that? Okay, and we have the two linear motion right here. You remember that? And the new part right here now. We have to, for the S and Y, we have the AS, the acceleration S, and acceleration Y, right? So we have the noise vector right here, as delta t squared over 2, and similar with the AY, delta t squared to ns delta t and ay delta t right here. That's the noise vector, right? And you know, in the acceleration, in the right here equal the new velocity minus the old velocity. This is final reverse divide to delta t, right? So we plug into the formula. We have this part. That's the noise vector, right? Acceleration vector. Without thinking, if the time delta t between the two new observations is long, this is more uncertainty, right? It's short time, it's low uncertainty, right? So the delta t and the acceleration, the two important things, impact to the noise, right? So we have this part. So look at this one. You can see random accelerator vector, the mu right here. They have for the AS acceleration s-axis thì đó là that's a normal distribution with the mean 0 and sigma square as and similar sigma square ay, right? So and from here mu we can decompose it into the matrix vector easily. You can see that for the as a y variable, and we have the new g right here equals ga. We can remember we got the coefficient right here, right? And we decompose two parts, g and a right here, and we define process covariance matrix. Its expectation. Yeah, I think remember the expectation in probability. So expectation, right? Is so from here we got the GA. We got the formula something like this, okay? And from you can multiply all the stuff together, you will get the process covariance matrix. That's really important. And we had to use this one for coding a calculation, right? Right now, we add this one into the formula Kalman filter for calculation, the process noise, okay? Okay, so after we already know how to calculate prediction S and covariance P, we continue to another step. There's update step, right? So update step, they had two phases. Right now, remember we use the fusion sensor. So for example, I assume we got the laser value first, right? So in the laser vector, so we use the Cartesian coordinate system. So we still apply for we still use the standard Kalman filter to apply update measurement. And how to do that? In the update measurement, you remember in the Kalman filter they mentioned Z, the measurement from sensor, right? H, the measurement matrix, right? And covariance matrix R. R is covariance, this noise of the measurement. Noise measurement right here is a noise from the equipment, from sensor. You can, right here is from the laser or it's from the radar. From manufacturer, they give you this number, what the uncertainty for your equipment, right? Remember that. Because right here we use the standard Kalman filter, right? So we apply standard Kalman filter for this case. But you will see next video I told you when we use the radar. When you radar, they use the polar coordinate system. So we had to apply. We don't use the Cartesian coordinate system. We use the polar coordinate system, right? And we had to they have to use for the circular motion. So you had to apply the extended Kalman filter in this case. So I will talk later in this video. So in this video, we just do this part, this branch first. We upgrade measurement for by the laser that are first, right? So how the laser data the apply in this case? So you see LiDAR sensor, they have the point cloud, and from point cloud you can use the object detection. I will tell this one in different topic for the point cloud detection, okay, and segmentation. And we got the object position PS and PY, right? And after that we have the measurement vector, right? Z, the measurement vector Z, we already have the PSPY. Remember, we are in the measurement update. You remember that? We got the Z right here, PSPY. And the state vector, we have PSPY and VSPY. PSPY, remember that people call the observable, and VSPY is the hidden, right? Okay, the measurement vector, I want to ask you, if we have a state variable PSPY for the right here, 4 times 1 in 4 row and 1 column, and we have the measurement vector right here, it's 2 times 1, 2 row 1 column. So what the measurement matrix right here, what the measurement mapping from 4D to 2D, right? It's easy, you know, in linear algebra, you know, 4 times 1, right? It means right here 2 times 4, right? You multiply together, you got the 2 times 1, 2 times 1, okay? So look at this one, which one is correct? What do you think? What the H right here? Let's give your linear algebra skill, look at it and you know D is the question, D is the answer, right? And one more thing, into the measurement update state phase, we know we have the noise, the measurement noise. Measurement noise right here, it had to be the 2 by 2, right? Covariant matrix. Because our noise vector have the same dimension as the Z, so it had to be 2 by 2, and the value right here, sigma square PS, sigma square P Y right here, you can get from the manufacturer of the equipment, the sensor manufacturer. So in this case, you can go to the brochure or the manufacturer to get this value and plug it in. That's uncertainty of the equipment. So far, we already checked. We know we checked the detection, okay, and we use the state Kalman filter and to update state and predict the state. Right here we have the 4D, right? Remember we have the 4D right here, PS, PY, and VSVY, right? So, and I talked to you before a little bit about right here before we jump to the coding, the C++. Right here, you remember the yellow right here, the data you get from where? The data you get from the laser sensor, right? The LiDAR. And there's another green one. It's a real path of the object of the detection. They go like this. How the Kalman filter estimate is matched really close to the real path, right? So what happens if the measurement for example, the measurement covariance matrix increasing? It means what happened if the sensor had error or the big uncertainty from manufacturer. So we increasing. You see, the Kalman filter is really not correct anymore, right? The Kalman filter estimate is not correct anymore. When we increasing the value right here, the manufacturer uncertainty of the equipment to right here, the value is different. That's the one thing I want to mention the result right here. The second thing, you look at closely right here, small part right here. So the Kalman filter compared to data, the laser data, and the real path is really linearly, right? It's straightforward, right? It's linearly, right? So it's very close, it's really good, right? So, but when the pedestrian he's, he tried to go to the curve or circular, so the common filter he something wrong, right? Because we apply the standard common filter. This is for the linear motion, right? He tried to go to straightforward. It's not applied for the circular. So what happened in this case? And how to solve this problem? Okay, that's really cool, right? That's the reason we use the fusion sensor. We apply the radar data right here. Because the radar data gives you the polar coordinate value, right? So we will talk more about this in the next video. Because in the fusion sensor, you have to combine two steps. The first step, remember, the first step from LiDAR sensor, the second one from the LiDAR sensor for update measurement to correct the movement of the state of the pedestrian. Not only go linear motion, go straight for right here, maybe go to circular, right? But summarily, I told you really basically the map, how to apply the extended common filter for tracking pedestrian. It's really when you run the code and you apply what you learn here, you get the result. It's really good. It really good result estimation, right? Really cool. And okay.